All right. 9.1, Chapter 9, Correlation. So, what type of relationship exists between two different variables? You could have a positive relationship, meaning as one variable increases, the other variable increases. So, a scenario where that might be the case, you could have study time, how much time you spend studying, and then your test grade. Maybe that's positively correlated, right? Maybe it's not, I don't know. But the more you study, the better you make on your exam grade. That would be a positive correlation. A negative correlation might be how fast you travel. So, speed of travel. Okay, as your speed goes up, maybe your gas mileage, your gas miles per gallon goes down. So the faster you go, the quicker you burn through your gas. And so instead of maybe getting 20 miles per gallon, maybe you're getting like 12 miles per gallon if you're really booking it, right? So the faster you go, the less you get in miles per gallon. So what is this going on here? We're doing a correlation. This is a relationship between two variables. Okay, so like here's a variable, here's another variable. Okay, here's a variable, here's another variable. A relationship between two variables, typically represented by XY pair. So like in algebra, when you plot a point, X is your independent variable. This is the explanatory, the explained, and Y is dependent. It's dependent on what? It's dependent on what you plug in, X. This is the response. Okay, the response. All right. So what we're going to do, all right, we're going to use a scatter plot. And this helps us determine correlation. Is there positive correlation? Is there negative correlation? There could be a scenario where there's no correlation at all. So like a scenario I can think of right off the top of my head, height versus IQ. Okay, so the taller you are, the smarter you are, maybe. Taller you are, the dumber you are, maybe. Right? So your height doesn't determine how smart you are, and how smart you are doesn't determine your height. There's no correlation. So you could have a third scenario where there's no correlation going on between the two variables. So your scatter plot's going to give you an idea of what type of correlation you have. So if it looks, your data when you plot it looks something like this, where Y is the dependent and X is the independent. So independent. Then this would be a positive linear correlation. It's a positive linear correlation that's going up like this in a linear, in a line fashion. That's what linear means. If I had another scatter plot and it looks something like this maybe. Okay, it looks like we're going down in a negative linear correlation. Okay, as X increases, it gets bigger and bigger. Your Y is decreasing. Over time, you're heading downward. Okay, with a positive correlation, as X increases, Y is increasing. Both are going up. All right, we talked about this, but if I have a scenario where it looks something like this, it just looks like random dots. Okay, this looks like, I don't know, no correlation at all, right? No correlation. Okay, a scenario here doesn't look like there's any random pattern, just looks like a random shotgun blast, okay? The last scenario, this is the one that might trick students up. Looks like this here. And you look at this, if you see a pattern like this, okay, you might be tempted to say, well, it's not positive because this side's going down, and it's not negative because this side's going up. So there must be no correlation, right? But does it look like there's no pattern at all? I don't think so. It looks like as you go down and then all of a sudden you're going up, there's a pretty tight band going on here, okay? So there does look to be some pattern, except for it's not linear pattern. It's a non-linear. It's not a line, but it is a correlation going on. Some relationship between two variables. That relationship just doesn't happen to be in a line pattern. Okay? So to give you an example of how you would plot, say you had like number of years work experience versus annual salary in thousands. Right, so if 1 year experience, 18,000, 4 years experience, 22,000, remember 22, and in thousands I put 3 zeros. 8 years experience, 30,000, and 15 years experience, 45,000. So reading from left to right, when we look at this, I'm going to plot my X on the vertical axis and my Y on the horizontal. Now, X is usually time. Time is your independent variable. Time's going to march on whether you want it to or not. It's independent of how you feel. So let's mark these as ordered pair. What's my first ordered pair? It's 1, 18. What goes with 4? 22. So I have 4, 22. Then I have 8, 30. And last I have 15, 45. How to plot. The first number tells me how far to go over. That's the X number. And the second number tells me how far to go up or down. Okay? So left or right for the X and up or down for the Y. All right, so we'll connect those together like that so there's no confusion on our arrows. Okay, so what do we have? 1, 18. So I have a 1, I have a 4, I have an 8, and I got like a 15, right? I know that's not to scale, but you know, whatever. Okay. Then, let's see. Well, maybe I should make this to scale. I know I go between 1 and 15. So let's mark out, let's do count by 4s. 4, 8, 12, 16. Okay? This other one starts at 18 and goes to 45. So I need to get up to like 50. So I'm going to do 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. So my first point is 1, 18. So 1, 18 is like right there. 4, 22 is like right here. 8, 30 it's like right around there. 15, 45 somewhere in here. So what does it look like on the long haul? What type of relationship do we have going on here? So this is a 1, 18. This is a 4, 22. This is an 8, 30. And this is a 15, 45. It looks like a positive, when your years of experience gets bigger, your salary looks like it's getting bigger, which is a good thing, right? Looks like a positive linear correlation. Okay? Now, it looks like is very subjective. This is subjective. Okay? It may look linear to some people, it may not look linear to other people, right? So we want some mathematical way, instead of saying, well, it looks like a positive correlation, we want to say, here are the numbers say it's a positive correlation. That way we don't have somebody trying to manipulate the truth, okay? So the correlation coefficient is a measure of the strength, okay? The strength, meaning the closer we are to 1, okay, or negative 1, we're stronger, and the direction, if it's a positive number, it's a positive correlation. If it's a negative correlation of the linear relationship between the two variables. The symbol rho, okay, the symbol R represents the sample correlation coefficient. Now, R is a little complicated to calculate. It's N times the sum of X times Y minus the sum of X times the sum of Y over the square root of N times the sum of X squared minus the sum of X all squared multiplied by the square root of N times the sum of Y squared minus the sum of Y all squared. Told you that one is pretty challenging, to say the least. So don't do that. Don't do it. Do it in your calculator. Let the calculator do the work for you. Okay, let the calculator do the work. Okay, so if I let the calculator do the work, that's all I got to do to it. Now, this is for the sample correlation coefficient. The population correlation coefficient is rho. Kind of like row your boat, right? So it's rho. That's the population correlation coefficient. So kind of like mu gets us x bar, and p is p hat, and sigma is s, rho is r, okay? R is between -1 and +1. Those are the values that R can be. R is between +1 and -1. So I'm going to show you, I'm going to do 6 charts, 6 graphs, and show you all the different values, different possibilities you might run into at R. So say you have a scenario, a perfect line. What do I mean by that? If I draw a line, it runs through all the dots. Maybe this is represents, this axis is the number of movie tickets. Okay? So no matter how many movie tickets you buy, the price is still the same. You don't get a discount for buying 10 tickets versus 1 ticket, right? So total cost. So if it's $10 to go to the movies and there's 2 people going, that's $20. If 10 people are going, that's $100, right? If one person's going, it's 10, then 20, then 30, then 40, then 50, and so on. 1, 2, 3, 4, 5. Okay? This is what's known as perfect. It is perfect positive correlation. This is an R equal to 1. R equal to 1. That's perfect positive linear correlation. Now, maybe it's not perfect, but it looks like it's pretty strong. That would be a strong positive correlation, linear correlation. So maybe this is like an R equal to 0.82. I'm just making up those numbers there, but 0.8 region, that's a strong. So maybe it's like person's height versus shoe size. So maybe the bigger they are, the harder they fall, right? No, the bigger they are, maybe they have a bigger size shoe, right? So, but it's not always like that. You could have a really short person that has a really large shoe, right? So, their height's not too big, but they got a really large shoe size. Okay, so it's not a perfect line. They don't all fall on the line, but it is definitely a positive, strong correlation. Okay. Another example, you could have maybe something like this. Right? It looks like it's more spread out, but in general, it's heading on the uptrend. This is a weak positive correlation. A weak positive correlation might be an R of like 0.35. Okay, an R of 0.35. Okay, I don't know with this one. This might be like income versus how much money is spent on, I don't know, milk. So maybe some people, like, the more money they make, if I just had more money, I'd buy me a whole lot more milk, right? But then there's other people, it's like, I could have all the money in the world, but I'm not going to buy any more milk because I just don't like it. So it's not a very strong positive correlation, but maybe there is some positive correlation. Okay. The other scenario, if I had, instead of being a perfect positive, you could have a perfect negative. So perfect negative. This would be R equal to -1. So once again, okay, the closer our R becomes to 1, the stronger the correlation is. If R is equal to 1 or -1, then guess what? That's a perfect correlation. This rarely happens, but it is possible, okay? An example of this would be like, maybe this is like the number of incorrect answers on some multiple choice test, and this is your exam score. So as your number of incorrect problems goes up, your exam score goes down, right? Y'all know how that works. So that'd be a perfect one if they were like, 5 points apiece or whatever. Something that's not perfect, but it still looks like a pretty strong correlation in the downward trend. Okay, this would be a strong negative correlation. Maybe an R of like -0.91. The negative tells me I'm going in a negative trend, so this is be like maybe the number of absences. Number of absences versus your test grade. What I've seen over the semesters is the people that miss more classes, they end up making a pretty bad grade. But every once in a while, I'll get somebody that's missed several classes, but they still have a good test grade. So there are those outliers. I will admit there's outliers that can do it. Now, maybe, this is their second, third, or fourth time taking the class. So, but nevertheless, there are some people that can miss a lot of class and still do okay on the test. Okay? And last, you've got the scenario where it just looks like a bunch of random dots everywhere, no pattern at all. When there's no correlation, when there's no correlation, what do we have? Well, perfect positive is 1, perfect negative is -1. If I had to draw a line to predict, I would draw a line just like this in the middle. And it turns out this line right here represents the average. And that slope there of that line is equal to 0. Okay? So if I get an R close to 0, that means I've got basically no correlation between the two variables. Non-correlated variables. If you're talking about, say for example, in the stock market, it's a good thing to have a diversified portfolio. One, because when you have crazy stock market activity like you've had the last couple of weeks with the coronavirus, your whole portfolio won't drop down as dramatically as if you're in one asset class, right? And so another reason that it's good to have non-correlated assets is because when it lowers that volatility, it can lessen that pain, and you can, as they say, weather the storm better, emotionally at least. So that's something that stock pickers and portfolio managers look for. They look for variables. They look for stocks that are non-correlated with each other. So like if one goes up, the other one's not going to go up just because that one goes up, or if one goes down, the other one's not going to go down just because that one does. And so it's a good thing to think about if you are going to plan on your retirement. How do we do this in our calculator? Okay, how do we do this in the calculator? So first, you've got to turn on diagnostic on. So before you do anything, get to the home screen of your TI-84. Then you're going to go to second, catalog, and hit the 0 button, and then scroll down till you see diagnostic on. Hit it, hit enter, and then you should see the word done appear across the screen. Until you do that, it will not output the R value. So I'm going to get students that are going to say, how do I get R, Mr. Clark? My calculator's not working. And I'm going to say, go watch the video in 9.1, and somewhere in that video is going to tell you how to find R. Well, this is where you find R. This is how you do it right here. You got to do these steps. Otherwise, it's not going to tell you what R is. So once you do those steps, okay, now you're going to enter the independent data into list 1, L1, and then you're going to enter the dependent data into list 2, L2. Once you do that, and to do that, all you got to do is hit the stat button. Oh, it won't let me highlight. The stat button, and then edit, and that will get you to list 1 and list 2. Okay, no big deal there. Then once you do that, once you got it inputted, you go to Stat, Calc, LinReg AX plus B, and hit Enter. And guess what's going to happen? It's going to have an output, and the output's going to tell you everything you need to do. You don't have to do any math for this remainder of this stuff here because it's all done in your calculator. You're not doing it by hand. It's going to say Y equals AX plus B. It's going to have A equals, B equals, R squared equals, and R equals. Now you're not going to see those last two things unless you run through what I told you to do right here. Okay, if you don't do that, then you're not going to see R squared and R. So you've got to do that before you run this. And when you do this, what is it going to do? It's going to output your A value. So it's going to give you a number here, a number here, a number here, and a number here. That first number is the slope. The number in front of the variable is your slope. the slope of the line. The b here, this is my y-intercept. Okay. This one is the coefficient, r squared is the coefficient of determination. Okay. And the last one is the correlation coefficient. The correlation coefficient. This is the one that we are wanting for this section. This one here, this is section 9.3. All right, so when we do section 9.3, you'll have to find this. It's no big deal. All right, the calculator does it for you. All you got to do is write down the number. Okay, in order for a correlation coefficient to be significant, right, the absolute value of R has to be close to 1, all right? So when I calculate that R, it needs to be close to 1. If we're close to 1, we have some strong relationship. There's a strong correlation. To determine if rho is significant, we use critical values in the table below. Now there's n pairs of data. Remember you had your x, which was your independent, you put in L1, and your y, your dependent, you put in L2. They're paired data, so this would be one data point, x, y, okay? So n pairs of data. If the absolute value of R is greater than the critical value that you find in this table here, then there's enough evidence to decide that the correlation is significant, okay? Otherwise, there is not enough evidence to decide that the correlation is significant, okay? So I'm going to run the numbers, and my calculator spits out this number right here, R equal negative 0.982. Is the correlation coefficient significant? Yes or no? Alpha 0.01, 10 pairs, n equal to 10. So how do I do this? I literally go to my n equal to 10 here, and alpha 0.01, so that's this number right here. So I get R naught equal to 0.765. 765. What's the test say? The test says that if absolute value of R is greater than the critical value, absolute value of R greater than the critical value. The absolute value of R, that's the absolute value of negative 0.982. Greater than 0.765. So is negative, what does the absolute value do? It gets rid of the negative. So is 0.982 greater than 0.765? Yes. So what does that tell me? There is enough evidence at 1% level of significance, alpha equal to 0.01, to conclude that that correlation is significant. So this tells us only that correlation is significant. It's not telling us the direction, just telling us that it's significant here. Okay. All right. The t-test can be used to determine whether the correlation between two variables is significant. The test statistic is R. The standardized test statistic is T equals R over the standard deviation of the correlation coefficient. This is R divided by the square root of 1 minus R squared over n minus 2. Okay? It's a t distribution with degrees of freedom equal to n minus 2, where n is equal to the number of pairs of data. Okay, number of pairs of data. So here's my table. It's the t distribution table that you already have. All right, so we've got a problem here. The weight in pounds of 8 vehicles and the variabilities of their braking distances in feet when stopping on a wet surface are shown below. Use alpha 0.05. Is there enough evidence to conclude that there is a significant linear correlation? So do we know that there's a significant linear correlation? Yes or no, right? All right, here's our numbers. What I'm going to tell you to do is I want you to put this into list 1, the first row. The second row, put that into list 2. Okay? So I'm going to test this. I'm going to see if I can do this on this calculator. I've never done it before. I'm going to quit out of this. Let's see if I have to do the home screen, second catalog. Uh-oh, is it gonna do it? Second catalog. Interesting. I wonder if it's even gonna run this. Okay, I can at least show you how to enter it into my list. Okay, so I'm gonna go up. I'm gonna clear out this list. I'm gonna type in the numbers. 5890, enter. 5340, enter. 6500, 4800, 5940, 5600, 5100, and 5850. All right. Now I'm going to go to my L2. I'm going to type in 2.92. You got to line them up. Okay, they gotta match up. If one of your columns when you finish isn't the same as the other, then you might have skipped one. It's easy to hit a wrong button here. 2.22, 2.88, and then 2.53, 2.32, and 2.78. Hopefully I didn't hit any wrong keys in. No telling. All right, no telling. So what can I do? Try going to stat and then going to calc and linreg ax plus b. Okay, and then it automatically inputted L1 and L2 for me. So let's see what it does here. All right, it tells me, oh, this is so cool. All right, it tells me from the calculator, it tells me what R is. Okay, awesome. So here's my hypothesis test, the ho and the ha. All right, I'm testing to see, is there significant linear correlation? Okay, is there significant linear correlation? That means that my correlation is not equal to 0. So significant linear correlation is not equal to 0. We're not saying, is it significant positive linear correlation? So significant correlation. All right, that's you know, the what I'm trying to see, is this true? That's the claim. So the ho is rho equal to, that would be no correlation. So what are we doing here? We're assuming that there's no correlation, and if the evidence says, buddy, there is correlation, then by golly, we are going to conclude that there's correlation here between the braking distances and the variability. Okay, variability in braking distances versus the weight of the vehicle. It would make sense, right? The more a vehicle weighs, the more variability, maybe. I don't know. So, I'm not a trucker, right? So that's a two-tailed test. Two-tailed test here. Okay. T is equal to r over square root 1 minus r squared over n minus 2. If you use your calculator, you got the r and the r squared already. Okay. Oop, wrong way. So this is like 0.95516 over square root 1 minus 0.95516 squared over 8 minus 2. So there's 1, 2, 3, 4, 5, 6, 7, 8 pairs, n equal to 8. Okay. When I type that in my calculator, I get 7.9018. Okay. A t-score of 7.9. Man. Let's see on our graph before I start saying anything. So zero's in the middle. It's a two-tailed, so I have a negative t-naught and I've got a positive t-naught. My alpha is 0.05. It's a two-tail. Degrees of freedom is 8 minus 2. That's 6. If I go look that up in the t-chart, I'm going to get 2.447. So 2.447 and negative 2.447. Okay. Now, where in the world is my standardized test statistic going to land? It's going to land like way the heck out here. Like 7.9. I'm pretty sure we're going to reject the crap out of that thing. Okay, so that hoe is definitely lying. So the null hypothesis, HO, is rejected. Okay, definitely. Way out there. So when we reject that, why do we reject? Because the test statistic is big time bigger than 2.447. All right? So what does that mean? That means there is enough evidence at alpha equal to 0.05 to conclude there is a significant linear correlation between vehicle weight and variability in braking distances. On a wet surface. Okay, so if you ever get in a wreck and police ask you, well, how fast were you going when you got in the wreck? You might as well tell them the truth, because they have computer programs developed by statisticians who inputted lots of data so that they could say, okay, we just measured the tire marks on the road from the skid marks and it went like 25 feet worth of skid marks. That means this car that weighed X amount actually was going like between 75 and 85 miles an hour at this point. So you don't tell them, no, it's going 60 just like the speed limit. You don't lie to them, because whether you lie to them or not, they're going to figure out how fast you were going, okay? Because all they've got to do is input those numbers into a little computer and it tells them how fast. So if you're lying to them there, then they're just going to assume you're lying about everything. So it's best to just be honest with them and tell them what's up. Okay? All right, back to statistics. Actually, I'm going to do this last part in one more